So welcome to this BCN Analytics event. My name is Didac Fortuny. I am data scientist, and I have been member of BCN Analytics for the last many years. I don't know how many. And well, today is the second episode of the Data and Sustainability series. Before starting, just give you these hashtags here. If you want to comment something about the event on the social media, you can use these hashtags, in particular if the comments are good. You will find during my initial presentation, you will have here also the hashtags for you to use. What is BCN Analytics and what we do? BCN Analytics is a non-profit organization. We here are volunteering, and this organization was created more than 10 years ago. And we combine data, BCN, Barcelona, and also social issues. How we combine these three topics? By organizing events like this, meetups about data and analytics. We try to organize at least a couple of events each year, but we are open to organize more of them if possible, and also datathons. In particular, the last datathons that we organized back in 2018, we organized this datathon to predict air quality in Barcelona, thanks to the help and the data from the Barcelona Supercomputing Center. And a couple of years ago, here in Adevinta, we organized another datathon about detection of racism in social media. My colleagues have the appropriate T-shirt. And this is like a new announcement today. We are preparing the new datathon that hopefully will be this year, at the end of the year, about the price of housing in Barcelona. We are open to ideas, to help, to any input or feedback. So if you feel that you can collaborate with this, contact us. You can find us in LinkedIn and X. You can write there a message, or you can write to any of the members of BCN Analytics that currently are these 4 people here. Pau Agulló, Manuel Bruscas, Ana Julia, and myself. Some of us are here. You will find us with T-shirts, and that's all. You can talk to us if you think you can contribute or you want to know more about BCN Analytics. As I told you in the beginning, this is the second episode of the Data and Sustainability series. This means that there was a first episode some months ago, and let's recap. In the first event, Pablo Rosado, who is also here in the audience today, already showed us some figures about climate change. She showed, for example, the rise of the global mean temperature during the last decades. Also, we saw the geographical distribution of these warm anomalies spread mostly around the world. And also some of the distributions and the evolution of some of the drivers of this climate change, in particular the carbon dioxide. And apart from this fantastic overview that we had in our last event, we have seen in the last weeks some headlines like this one. Last month, March, was the hottest March on record, and also was the 10th record-breaking month in a row. For all these reasons, we decided to focus this second episode of the Data and Sustainability series to climate change, to climate modeling. And here are some ideas that we will cover today with our amazing speakers. For example, we will see the difference between climate models and weather models. And at the end, it's a matter of scale. Climate models focus more on the evolution of means or statistical values, whereas weather models focus more on the prediction at a short-term, smaller scales, but I'm sure that our speakers will explain this better. We will see as well how the models are transitioning, both climate and weather models, from only including science, mainly physics and chemistry, to including also machine learning and AI tools. And we'll also see the modeling and analysis of some of the effects, of the side effects of this climate change. So don't worry. The agenda for today, before these actual talks, we will have a word from our sponsor, Adevinta, that is giving us this place to make the event. Marta Ros will give words about Adevinta. Then Anavia will introduce Data for Good Barcelona, that it's a sister organization that does also very cool things and who have an event in the next weeks. And I will explain this better than myself. And then we will start with the actual talks. Francisco Doblas-Reyes and Rachel Lowe from the Barcelona Supercomputing Center, and Ignacio Villanueva from RavenWits, and finally Ferran Alet from Google DeepMind will give us their impressions. At the end, we will have a common Q&A session in which there will be an open mic for everyone to ask questions to the speakers. And last but not least, at the other side of the corridor, we will have pizza and drinks, and we can discuss some topics that has not been dealt in the talks or whatever you want. So let's start, and please, an applause to Marta, who will give us a word about Adevinta.
Working? Yes. I'm also the party pooper because you're here to listen about data, and here I am to talk about Adevinta and where you are right now. So how many of you knew about Adevinta before coming? Cool. Most of you. Hopefully I'm going to say something new for you. So we are a leading online classified group, and we are champion for sustainable commerce, making especially positive impact, not only in the environment, because what we do mainly in our marketplaces is sell second-hand goods. So we have a positive impact on the environment by reducing the production of those, but also in the economy, because we have marketplaces that are offering also jobs, and also in the society in the overall. Right? So when we are talking about our vision, purpose, and mission, our vision is to create a healthy planet, society, shaped by this sustainable commerce. Our purpose is to help everything and everyone to find a new purpose. So when we are talking about everything, we are talking about the goods that are sold on our marketplaces. And when we are talking about everyone, we are talking about people that are finding a new future in their career. And when we talk about our mission is to create those perfect matches through the locally loved brands, but also made in a global scale. So I'm not going to deep dive on the whole story of Adevinta because it's super long. Indeed, we were beginning our history even before internet was created, and we come from two different paths, right? From Adevinta and eBay, and they were merged in 2021. So now eBay is more known as Kleinanzeigen, and you will see the brand. But mainly we have been growing throughout acquiring different marketplaces that are number one in the different markets that they perform, right? So when we look the big numbers, we operate both in Europe and America with more than 25 marketplaces impacting 2.5 billion of users coming to our platforms, operating in 10 different countries. But if we deep dive in Europe, which is what we work mainly here when we are talking about product and tech and the products that we are developing, this is where we are mainly present. And you can see that we have like two different type of marketplaces. The ones that are like more specialist, and here in Spain are well known like Habitaclia or InfoJobs or Coches. And then we have others that are generally, so we sell everything there, and we have different verticals that are also dedicated to these specific topics like real estate, mobility, job, and those are here in Spain, or in Italy, Subito, Leboncoin in France. But we are not only about working and building marketplaces. We are also a company that are made essentially by human beings, and these are the values that drive us. First one is experiment bravely, and this is not only about A/B testing in our products, it's also to challenge the status quo of the way that we are working. It's also about acting for maximum impact, but not only the impact on the revenue of the company, but also on the impact on the environment, the economy, the people that we are working for. It's also about using our voice to express what we think that needs to change or whatsoever, and also being open to listen and grow through different perspectives and acting as a team, right? Like win together and lose together. And when we are talking about teams, one of our values is diversity, equality, and inclusion. We are really committed to that. Indeed, I'm wearing one t-shirt of Women in Tech. That is one of the initiatives that we have internally in Adevinta. And it's not only about the way we work and how we build our workspace, but also about our marketplaces. So as Didac said, I'm a product director in InfoJobs, and we are very proud of having a platform that is trying to make the hiring process more diverse, equal, and inclusive. And now I'm going to give the opportunity to Anna to talk about the next topic.
Okay, thank you, Marta. No?
Please.
Okay, thank you, Marta. Now Ana Vía will present Data for Good Barcelona.
Okay, so this is Data for Good Barcelona. First of all, thank you so much, Barcelona Analytics, for letting us have 2 minutes to introduce our project and our next event to this amazing public today. We are also a nonprofit organization formed by volunteers, and we have 2 main goals. The first goal is to connect the third sector institutions, so NGOs and so on, with the data community, mainly to help these NGOs and entities to leverage better their data, but also to get the data people closer to the realities of this third sector and like understand how we, from a data perspective and technical people, can help them. Here you can see some of the institutions or entities, NGOs that we have participated with in terms of projects. Maybe you know some of the names like Stop SIDA, FADA, Down Catalunya, and so on. And our second goal as a community is to actually do something similar to what is doing today Barcelona Analytics, which is organize events. In that sense, our goal there is to organize events that help generate further awareness to the data community in terms of data for good projects, ethical use of or responsible use of data and AI and so on. And the news here is that we are organizing a super cool event that will take place also in Adevinta on May 7th, which will be about the responsible use of AI. Similarly to, again, Barcelona Analytics that is exploring through a series of events the part of climate change and so on. We are exploring with a series of events the ethical and responsible use of AI, mainly as an excuse or not for the fact that AI Act is coming and is already being approved, and it will impact for sure like how DS and data are using AI in like digital products and so on. And in this case, like our second event will be, we'll have two talks. The first one will be from Christian Pachon around model explainability, so importance, benefits, and limitations. And the second one will be from Axel Brando around trustworthy AI in real systems, so security, trust, and responsibility. You have the QR. I've seen a lot of people taking out their phones, which seems interesting in terms of, I hope that this generated some interest to you. And yeah, that was it from our side. Hope to see you in our next event in May. And thanks again, Barcelona Analytics.
Thank you, Anna. Okay, so the first talk of this evening is by Francisco Doblas-Reyes and Rachel Lowe. Francisco Doblas-Reyes is a researcher in experimental sciences and mathematics and the director of the Earth Sciences Department at Barcelona Supercomputing Center, Centro Nacional de Supercomputación. And Rachel Lowe is an ICREA research professor and Global Health Resilience Group leader. She also holds a Royal Society Dorothy Hodgkin Fellowship at the London School of Hygiene and Tropical Medicine. Francisco will present a new approach for the development of user-relevant climate information, the digital twins. And Rachel will outline the public health challenges posed by climate change and propose digital solutions to help build local resilience to emerging disease threats. So an applause and welcome to the stage.
Thanks, Didac. Sorry, I forgot the pointer. And thanks for the invitation to join here, and also to Manuel. This is not my comfort zone, I have to say. I'm usually much more comfortable surrounded by academicians and people who are doing pure research. I mean, research in that is basic research. But here I'm going to try to explain some novelties that are emerging in the field of climate modeling and also the formulation of climate information that can be more relevant to those that are vulnerable to climate change. So it's coming up, yeah. So the presentation turns around the concept of digital twin, and what I'm going to present here is part of an initiative funded by the European Commission called Destination Earth that brings together technology, supercomputing, and user requirements to try to address the field of climate adaptation. So how do we really get close to a solution that allows us to live better, if possible, or at least the same lifestyle that we are living right now in a changing climate? Because climate is changing. Last weekend, the temperature in Barcelona reached 29.4, I think it was, at the Observatory Fabra. So this is probably not a place suspicious of being very much affected by the urban heat island. And this is the maximum, the record temperatures recorded in that observatory that has been recording temperatures for more than a century. That was the maximum recorded temperature for a month of April in the city. And that might not sound like that much, but if we take into account that the record was beaten by almost 2 degrees, that was 27 point something, the previous one, one might realize that something is happening. And it's not nice, even if we enjoy going to the beach and on a day like that Sunday. The problem is that we are running out of water, and that doesn't really help. By the way, the previous record was the previous year. It was last year in 2023. So we are not going in the right direction, particularly in the place where we live. So we need to adapt. We need to first reduce our emissions and have a different way of burning fossil fuels and doing agriculture. But at the same time, we have to recognize that we have to do something for adapting our lifestyles, our economy, our ecosystems to this climate that is changing. And that's what I'm going to try to talk about here. So how do we provide some useful information for the decisions that are related to climate adaptation. Okay, sorry. So before, as my colleagues have done, and also speaking in the name of Rachel, I would like to introduce what we do. So we are we work at the Earth Sciences Department at the BSc. The Barcelona Supercomputing Center it's a national consortium funded by the Generalitat and the central government, and with the support of the UPC as well. And it has 4 research departments, one on life sciences, another one on engineering, computer sciences, and then our departments, where we are around 180 people working basically on weather and climate problems, including air quality and its applications. And we focus on specific problems that are target adaptation, modeling that is required to deal with adaptation. And for this, we count on a really great number of colleagues that covers fields that go from software engineering all the way down to philosophy of science. And all of them are really needed to really make sense out of the research that we're doing. Okay, so climate adaptation. So adaptation is the set of actions that are necessary to basically have a decision-making process that is properly informed and that takes into account how we have to live in a changing climate. And this adaptation problem is very much related to the risk assessments associated with climate and also the mitigation problems. So, for instance, if we decide to mitigate and reduce CO2 in the atmosphere by planting trees, this is going to have an effect on our adaptation decisions because trees need water, and this is precisely not something that we are really having in excess in this region. So adaptation and mitigation are very, very closely related together, and of course, risk assessment as well. This figure is from the European Climate Risk Assessment Report that was published last month. It's a report. It's the first report mandated by the European Commission. That was elaborated over 18 months. It was really tough preparing that, and it tried to assess the risks related to climate in all the relevant sectors in Europe and also outside Europe, but related to European interests. So Europe and its environment. It's not isolated. To do these kind of assessments in the same way as we do with climate adaptation, we need climate information, and climate information requires climate data, climate knowledge, and also knowledge about what the users pretend to do with this data. So it's not something that we can do in isolation. The old very nice days of climate modeling where mathematicians and physicists got together and had a great time trying to build a great computer program to simulate the climate are long gone. That doesn't really work anymore, and the European Commission has recognized this, and that's why it has funded this Destination Earth program. So far, the climate information that is available out there in the public domain and free for everyone comes from research-driven projects. These are international projects in which we also participate at the BSc, and that try to simulate what the global climate is going to do in the future, up to 2100 and beyond, because climate is going to keep changing for the next centuries. It's not going to stop in 2100. These experiments that provide the data for that estimate the evolution of the climate for the rest of the centuries to come is actually being prepared over several years. This is a best effort from the research community, which lacks something that is very important, is the operational aspect of producing this, which is something that we have in weather forecasting. And the same applies to other related experiments that try to produce this information at high resolutions, 10, 25, 50 kilometers in specific regions of the planet. All research-driven, very static, and and quite heterogeneous. So what is the community thinking on to move on from this very static way of doing things based on very great efforts from the research community, but are insufficient to provide the climate information that is required by society. It's operationalizing the formulation of climate projections. So it's making it professional, taking it not out of the research side, so we still will need research, but to have a completely different look at how these experiments are performed. And that implies starting from the user requirements, identifying what the financial sector actually requires in terms of climate information, which variables, which experiments, which regions they are interested in. The same with any other sector, hydrology, ecosystems, retailing, anything that you can imagine is actually climate vulnerable. So starting from those questions, we can start thinking and very hard and in collaboration with those users, which are the experiments that they really need and at what time and with what frequency they actually need it. So for instance, the European Commission, which is one of the customers of this exercise, goes to the Conference of the Parties, which are these massive events that take place once a year where they negotiate with the rest of the countries in the world what are going to be, for instance, the investments in adaptation at the level of $100 billion per year, or the commitments in terms of emission reductions for methane, CO2, and many other factors. Somehow the Commission goes there blindly and negotiates with China and the US without information that is updated. So when they make a commitment in terms of the reductions of methane, which is a gas that is very much related to oil production or residuals from urban areas, they don't really know what the effect of a certain level of reductions from China or the US is going to be at the global level. And this is something that we need to sort out. We can't really commit to trillions of investments in terms of emission reductions without having the tools to really go to those meetings and know what are the consequences of the decisions that politicians are going to make there. So, oh, sorry, that's the sound. It's thank you. That's basically what we are doing. So we are developing a completely new suite of climate models that run not in research mode. They run in a professional way. So they are developed completely as part of a whole suite of software that includes also the user requirements at the beginning of the whole thing. At the same time, we use climate models that are unprecedented in terms of resolution and complexity. So for instance, we are running these models at 5-kilometer resolution at the global scale, including the atmosphere, the ocean, the ice, the vegetation, and the land surface. So everything that really counts for climate. These models, the experiments that we are running are using machines like the new Mare Nostrum that we have at the BSc, or Lumi, which is a supercomputer in Finland, the largest now in Europe. And we've been using solidly 10% of that machine to complete these experiments. So it's really ambitious. It's very heavy in terms of computation. And it's very heavy in terms of data. These experiments produce 100 terabytes per day. And this data has to be used and consumed as the model runs. So we cannot wait a couple of years, as we have been doing in research, until we deliver this data to the users. The data has to be consumed on the spot. We have to do the most of the data that is being produced by these models. And we do this by incorporating the user requirements in the workflow that is producing these experiments. So we call this streaming. So we are actually streaming the model world to whoever wants to use this kind of data. Let me see if I can move on. Okay, so that allows us, for instance, to try to infer estimates of user indicators, user-derived indicators from these simulations straight away, and provides, for instance, histograms of the wind speed at hub heights for wind energy producers, which is basically what they want. They don't want long time series of simulations that are very heavy and they are distributed around the world, but actual histograms that they can convolute with the power curves of the turbines that they have in their portfolio of wind energy producing centers. What role for AI? AI is not able to produce or generate climate simulations right now. It can emulate trajectories simulated by the models that we are currently using, so models based on first principles. But AI can be very useful. And last year, with some colleagues, we tried to analyze what could be the role of AI in weather and climate research and operations. And one of the aspects that we found interesting is what was the role of research and what is the role in research and academia and what is the role of the private sector in AI for weather and climate. And interestingly, there is a very rich symbiosis that can take place there. So the big techs have been very active in producing, for instance, the first AI-based weather forecasting models. They are not climate models. They are basically weather forecast models that are competitive with the best one that is now the reference at the global scale based on the traditional way of making weather forecasting using equations. It's so good, what they have done so far, that actually now weather forecasting centers around the world are developing their own AI-based weather forecasting systems. We can leverage this kind of information and knowledge and develop the emulators of these trajectories of the future climate that we are generating with the physical models to deliver the data that we are producing in a much more targeted and simpler way. So if we build this emulator, which we are working on right now, which is basically the same model that the big techs have developed based on generative AI, we can produce the data that is actually delivered, that is required by the users directly in the regions and the variables that they actually want in seconds, instead of having to deliver masses of data that might take a few days to deliver. The other aspect in which the private sector has been very active is chatbots and large language models. And I don't need to mention any names here. One of the aspects that make climate adaptation very challenging is that it doesn't scale. So every single person, every single institution, every actor that is affected by climate requires a description of the future climate impacts on the sector or person that is personalized. That it really goes into the context and the values of that particular actor. And that can only be done either with a lot of humans or with the support of chatbots like the one we see here. Unfortunately, current large language models available are not particularly clever in the way they deliver climate information for adaptation. So what we are doing is basically what many other domains are doing. So retraining these models with the best thing that we have, which is data and knowledge. So we have a lot of data about what climate adaptation should be. We know what the climate adaptation plans at the local, regional, and national levels are. And we are training open source large language models to basically deliver the best service that society requires in terms of climate adaptation. So data, knowledge, and user requirements is basically what is driving us. Thank you.
Thank you, Paco. Okay. So thanks very much. I'm now going to speak a little bit about the impacts of climate change on health. So as Paco mentioned, I'm leading one of the groups in the Earth Sciences Department, the Global Health Resilience Group, and we're an interdisciplinary team of epidemiologists, climate scientists, data scientists. We're often looking for software engineers and data scientists, so do keep an eye out for any jobs we have coming up. And our mission is to co-produce decision support tools with different stakeholders, particularly ministries of health or humanitarian agencies, to try and translate the wealth of climate information that we have available at our fingertips into usable and actionable tools that can be applied on the ground to help guide interventions. So we're working with partners across the globe And we particularly work with government agencies like meteorological services or ministries of health or researchers within countries. We have many partnerships in Latin America and the Caribbean region, also parts of Africa, Asia, and Europe as well, where we're working to try and develop tools to either understand how climate is impacting outbreaks of diseases like dengue or malaria, and also trying to resist the emergence of these diseases in places like Europe. We know that in Barcelona, we have the Aedes albopictus mosquito, and the climate is becoming, as Paco mentioned, more and more suitable. We're starting already to see the first sightings of the Aedes albopictus mosquito this year. And we're also having huge dengue outbreaks happening across the globe, particularly in Argentina and Brazil. And we're having more travelers than ever arriving to Barcelona with dengue. So we're really at sort of high alert in Barcelona to try and stop onward transmission. And a lot of the work that we do in our group, we're working closely with different policymakers, and a lot of our work feeds into policy reports that are published by either the European Environment Agency or the World Meteorological Organization. This is an example of 2 reports we recently contributed to. So a couple of years back, we produced an analysis of different scenarios of how climate change and different demographic profiles could impact the burden of both malaria and dengue across the globe until the end of the century. And we found that if we're to continue as business as usual, emitting all this level of greenhouse gases that we're seeing at the moment, that we could see an additional 4.7 billion people living in areas at risk of dengue and malaria. And if we were to take concerted action and keep global temperatures below 1 degree C, which is looking incredibly unlikely now, then this number could be reduced drastically to around 2.4 billion. So there really is a lot we can do. And climate change is threatening our health, particularly in terms of infectious diseases, but also other health outcomes like food security, access to water, and heat-related mortality. This is an example of a study that we did looking at how climate change is impacting the changing burden of dengue in Vietnam. And if we compare the relationship between temperature and outbreaks of dengue in the last 20 years compared to a reference period from the 1950s to the 1970s, we can see that the risk of dengue really is increasing and that it's changing in seasonality, particularly in the north of the country that's traditionally cooler and has highland regions. We're starting to now see outbreaks of dengue spreading into these areas, and this is a pattern that we are seeing also globally. Our group is also contributing to an international collaboration, which is called the Lancet Countdown on Health and Climate Change. This is a collaboration led by UCL of around 300 climate and health researchers who are producing a series of different indicators to track the impacts of climate on health in terms of impacts, adaptation, mitigation and co-benefits, economics and finance, and political engagement. We contribute a series of climate-sensitive infectious disease indicators to this collaboration. And here, this is an image produced by Nature in a news article just showing the areas of the globe that are now newly suitable for the transmission of the 2 major malaria parasites. So how do we build these kind of indicators? We take a series of different data sources. For example, the Copernicus Climate Change Service produces different layers of hourly information, for example, on temperature, precipitation, humidity. We combine this with different layers, for example, to understand the topography, so we can monitor how these conditions are changing in highlands compared to lowlands. And we combine it with different data layers to understand how these different changing climate hazards interact with different levels of exposure and vulnerability. And this allows us to produce this suite of different climate indicators. But of course, these products are limited when you're looking at the small scale. So particularly if we're thinking about small island developing states, which are particularly vulnerable to climate change. If we're thinking about a particularly large island like the Dominican Republic, then these kind of products, this is a 9-kilometer grid. then we can pick up, for example, some of the topography on this island, and we could perhaps help guide some interventions. But if we think about the really small islands like Barbados, Grenada, or St. Lucia, then these gridded products are quite limited, and we really need to be working with the ground truth level meteorological station data to help understand how the meteorological conditions are varying on the ground and are in fact affecting the local population. So to try and address some of these data issues, we have a Wellcome Trust funded project called Harmonize. And the goal of Harmonize is to develop reproducible and cost-effective digital technology to be able to integrate these different data sources. So the satellite imagery, gridded reanalyses and forecast data. And we're strategically collecting ground truth data using both drones and weather sensors that we're installing in particular areas that we want to understand how the disease transmission is changing. So we're working with partners in the small islands, in the highlands of the Andes, in the Amazon rainforest, and also in cities across Latin America and the Caribbean, to integrate these different environmental and climatic data sets with socioeconomic and demographic indicators and also disease surveillance data sets, so that we can build the robust evidence base to then be able to build early warning and response systems. So how do we do this? When we're building our models, we're trying to integrate many different kinds of data that can help us understand how disease risk may change in space and over time. So we integrate a series of different Earth observations to understand different climatic and environmental changes and issues to do with land use and land cover. We can also integrate information to from a hydrological model to understand different aspects in terms of mosquito breeding and water bodies. And we use surveillance data. For example, this may be the counts of cases, the number of dengue cases in a particular province or municipality. And we integrate all this together in a series of different models. And then we can make predictions from 1 to, say, 6 months in advance by using forecasts of the climate, which allow us to then say what is the probability of an outbreak of dengue or any other climate-sensitive disease several months ahead. And we're working with partners to develop usable apps that can be integrated, installed on local servers to be able to integrate these data sets and produce this information on a routine basis. So we're currently developing a product at the moment. It's called Endcast, which is an El Nino-driven disease forecasting system. And we've been in real time monitoring the El Nino event that emerged in 2023 and how this is impacting the climate in hotspots in Latin America. We're seeing that this El Nino event is causing extreme drying in the Amazon and also flooding events, for example, in northern Argentina. So we're working with our partners in these different hotspots to produce this information that then is translated into alert levels from 1 to 6 months in advance. And we try to produce this information in a way that can be quickly acted upon and interpreted by our users. And we've been designing this through a series of different questionnaires and stakeholder engagement activities. We've also been working with partners at the European Space Agency to understand how different machine learning models can also help us understand and integrate these different multiple data layers. And we're currently working towards some model intercomparison projects so we can understand how the kind of Bayesian statistical models that we've been developing compare to different machine learning and AI approaches. And we're also developing a project at the moment with the Hospital Clinic here in Barcelona and the Public Health Agency to try and integrate the reporting of imported cases of dengue and other arboviruses into the city, and to try and develop some sort of risk indicator score to help the public health agencies know which parts of the city are most high priority for conducting interventions, such as going to the households where we have infected patients and eliminating the mosquitoes in those particular areas. So this is a work in progress, and I hope to be able to share that next time. So thank you very much.
Thank you. Thank you, Francisco and Rachel. And well, if you have questions, we will have time later for questions for all the speakers. So please remember them. But now let me introduce, well, okay. Ignacio Villanueva. He is a mathematician, full professor in Universidad Complutense de Madrid, researcher in functional analysis, quantum information, and machine learning. He also is CEO and co-founder of RavenWits. Ignacio will explain how deep learning's expansion into weather prediction will not only popularize and enhance the forecasting of weather-related variables, but also extend to improving predictions for renewable energy production. So, okay. The floor is yours.
Hi. Thanks. Thank you. So I'm professor of mathematics at University in Complutense. I don't have the kind of computational resources that my colleagues exposed, or the computational resources that Ferran will talk about later, working in DeepMind. So this will be kind of more a guerrilla approach to uses of machine learning, not in climate modeling, as Paco mentioned. As far as I know, machine learning models are still not useful or too useful for climate modeling, but I will stay in the short range, so that like 1 week ahead, and that's weather forecast or meteorology. Yeah. So I'm just like going to give you my take and my view on this. The quality of the presentation is the standard in mathematical conference, and it's really, there was a decay in the aesthetics. I'm sorry for that. But yeah. Okay, so yeah, data analysis has become one of the main characteristics of modern day technology. So it's something new. It didn't exist. We didn't have the access to that amount of data, or we didn't have the capability to manage it. And these things are developing very fast. We are getting access to more and more data, and we are developing new tools that were non-existent and non-imagined just 10 or 20 years ago. Not 100 years ago, but just 10 or 20 years ago. We were developing it fast. Machine learning still is in a engineering consideration, say from science. He mentioned the difference between a physicists and mathematicians working on their differential equations versus data fighters doing things with data. Still, I think science considers above that, but these things are becoming very blurry, and things are mixing soon and fast. When do we use machine learning at the present moment? It will change in 5 years, but what are the good candidates for the machine learning, basically? Where you don't have a model, you don't have a scientific model you can touch, but rather you have lots of data. So say you want to tell dogs from cats, so you have a model for a dog or a model for a cat, but you have a lot of data of pictures of dogs and cats, or in other languages. We have nothing like a model for language, but we do have a lot of data. And that's where the killing applications of machine learning are appearing so far. Where does meteorology sit here? In a way, it's special because we do have very precise models, very good, very well described. The differential equations are well known, but they're very difficult to solve. You do have butterfly effect, you need supercomputers just dedicated to this. And at the same time that we do have a model, we do have a lot of data, of historical data. We have huge amounts of information in the meteorological agencies. So in a way, you can try to use both. You can do science in the classical way, solving your differential equation. That's what weather forecast still does. And you can start doing it with data. Listen carefully to the next talk where Ferran will talk about what the DeepMind has done with GraphCast model. That is probably will become the standard soon. I don't know. Okay. So what's the machine learning approach to meteorology? I insist I'm not doing climate. I'm just doing weather forecast for the short range. just forget about the differential equations, no idea about their solutions. What you do is what you typically do in a machine learning setting, just set an architecture, flexible enough. You try to choose an architecture which is well adapted to your problem, and you fit in the data, and you help your architecture will learn the solution to the differential equation. So there is an underlying differential equation. You don't use it, you don't see it, you don't need to know it, and you just your intelligence will learn to predict something. In the global case, the whole variables of the whole world, that would be what's the weather forecast. The problem is difficult, it's non-trivial. You need powerful computational resources. The architecture that several architectures have been used, I think the best so far or more successful is graph neural networks. That will come in Ferran talk. But others have been used, and probably others will apply. Graph neural networks, as far as I understand, are good when you know you want to solve a differential equation, even if you don't know it. It is somehow based on finite differences methods and this kind of things. Okay, so now this is like a methodology global. What is this like downgraded methodology, or this guerrilla I talked before? If you want to predict the whole methodological situation, that's difficult, and it's still computationally expensive. But computational methods are becoming cheaper and cheaper, and this is how democratizing all this. So you get cheaper access to powerful resources. And if your goal is not so ambitious, you don't want to model everything, but you want to model small things, then maybe you already have access to that. So you don't want to know, or in many situations, you don't want to know the whole weather forecast. You want to know something. It's going to rain tomorrow at the beach. We do wind energy prediction. What will be the wind at this point? That will imply a certain amount of energy. Or what will be the maximum wind at an airport? So that is it will be possible to fly or not? So you may have local variables, meteorological variables, or meteorologically related variables that you might be interested in predicting. And until now, we did not have many. So doing that was expensive. It required a lot of resource. This is becoming cheaper, more available. Cheaper in not only economically, I mean conceptually. It's easy and it's not too costly computationally. So let us look at it from the. I don't want to make a technical talk at all, but just from the high-level structure of what we are doing. We have a problem. We're going to solve with data without imposing a solution. We don't take into account what the underlying model might be. We don't know it. We just want to use the data and the data. And so you do what we typically do. You need to know what your input is. You need to know what your output is, or the output you want to predict, and you want to train a model to do that. In our case, what is the input? Oh, sorry. The input is numerical weather prediction. When you hear about a weather forecast, what is a weather forecast? Well, I didn't know what was a weather forecast a few years ago. Weather forecast is just you get a lattice of the planet. Surprisingly, Earth is not flat, so the lattice is not perfect, actually, but yeah, close enough. So you can sort of a rectangular lattice of points covering the planet's surface. And from the model of the European Center, there's a standard is every 0.1 degrees. That would be like 10 kilometers in our latitude. So every 10 kilometers is to west and north to south, more or less. You get a point in your lattice, and for that point, you get a column of altitudes, surface level, 100 meters, 200 meters. I don't know them all at all. And for each of these points, you get several variables: temperature, wind, pressure, humidity, blah, 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 blah. This is a huge amount of points with a huge amount of numbers. You will not need them all, but that's what you get. And for the purpose of this talk, what is interesting about that, that's extremely similar to a picture. So points on the map, you can assimilate them to pixels. The color channels in a photograph, in a picture, is like meteorological variable. So at the end, you get a rectangular lattice of points, and at each point, many numbers. Okay, and we have learned to deal with pictures. So some of these things could be useful. So that was for the input. What is the output you search for? Well, depends on what you want. But what would you need? You will need data. So essentially, what is becoming easier and cheaper in many senses to do is to pick your favorite meteorological variable or meteorologically related variable that is not included already. Of course, if the weather agencies already gives you that variable, then use it because it will be unbeatable. But if it is not included, you will need data. So you will need some device, a thermometer measuring temperature, an anemometer, or whatever you will need to get some quality or some estimate, or high quality estimate of the output you're looking for, or a variable dependent on it. In our case, it's going to be energy produced by a windmill. Could be rain at a pluviometer, whatever. Okay, the flow of a river. Yeah, and then what do you do with this? You take your historical numerical weather predictions with historical labels or outputs. You choose an architecture adapted to your problem. The main tools, as far as I know, you've been used now. This would be convolutional neural networks. That's what we started using in 2010, 2012 to deal with pictures, with images. That's where all these generative image things is coming from. Graph neural networks, they are newer, but they seem to be very adapted to this problem. This is just the old-fashioned multi-layer perceptron that is still extremely useful for many purposes. There are even transformer is the architecture that is the foundation of ChatGPT and these natural language processing things, architectures. And the transformer is the underlying cell. And there are even transformer-based architectures for this kind of problems because they can understand relation between faraway points. And then just train your model and test it and see if it works. Okay, and this approach, that's what I'm trying to say, that is, I think it's going to become more and more general for many situations, mostly because it's very cheap in a way to do it, and it's very effective. So I'm here because of a use case of this. There is wind energy prediction, and that's what we are doing. And we founded a company recently where we do these things based on exactly what I'm telling to you now. Renewable energies, particularly wind, are very difficult to predict. The average error you made in the prediction 24 hours ahead of a wind park, you have a wind park, you want to know how much energy is going to produce tomorrow, because you have to sell that energy, because you have to tell the other agents how much energy you're going to put into a system so that everything is prepared. If you are not going to put enough energy, that there is a gas plant that needs to be warmed up to be ready in case you are not, blah, blah, blah. So, and this is done typically in 24 hours ahead, many of these things. The error is the order of 30 or 40% of the mean production of the park. I mean, the error is huge. And this makes life difficult for the transmission system operators, Red Eléctrica in Spain. And it makes it difficult to integrate larger and larger amounts of renewable energy. We want to put a lot of renewable energy into the system to stop CO2 emission, but you need to deal with it. You need to be able to handle it. So for the normal people, it's a zombie apocalypse. For the TSO, is a blackout. A blackout for them is chaos total. This cannot happen no matter what. So, and for this, I didn't know, but in the electrical grid, you need to fit in exactly as much energy as you are demanding. You cannot put less or more because you get a blackout. So things have to be very well calibrated, and it's not easy. And so to integrate larger amount of energy, you need good predictors. And well, because it is bad for the system, it is penalized economically, and yeah, as I say, better predictions will allow for more use of renewable energy, less CO2 emissions, and more money for plant managers, which is okay because so they can make more plants. So we started doing this with Red Eléctrica Española, that's the Spanish electrical TSO, the transmission system operators, that are in charge of the electrical grid. And they tried this was in the literature around, and so they wanted to try the machine learning way to as a proof of concept to forecast wind energy production. And yeah, we started doing it in 2019. A research project they financed, and it was a great success. The models were pretty good from the very beginning, which basically means that the technology was good for it. And we've been collaborating with them for the last 5 years. Since then, we have further developed the models. We have refined them. We have industrialized it. So we've made models for each single wind park in Spain. There's like over 1,000 of them. We're doing also photovoltaic prediction, try to deal with uncertainty. And yeah, we founded a company with all these things, trying to get more resources, because even though I'm saying this is cheap computationally, at the end it's not so cheap. And at the end you need resources, you need money for computation, and you need people doing code. And coding is takes time, even with ChatGPT, it still takes time, too much time. And yes, I will not go into technicalities, just say which are the architectures we are using. So mostly, for those of you who might be interested in convolutional neural networks, we convolute not only in space, but only in time. So you get the prediction of what's going to happen now, the previous hour, the next hour, and you can convolute in space or in space and time. We use graph neural networks this recently, just actually since the paper Ferran will talk about later. Since that paper appeared, we started trying with graph neural networks, and they work very good. Just perceptron. We use data, the numerical weather predictions from the European Center. This is American, GFS. We also use the German and France agencies. We have 30 terabytes of historical data. For us, it's a lot. Paco mentioned they generate 300 terabytes per day. So my problems are different. But yeah, still for us, it's a lot. Just to keep it. I mean, Amazon Web Services charges you a lot to keep that in a somewhere. And we just fit in with a wind. We plug in the wind at 100 meters. That is the height of a windmill, and the two components, and that's the things that we fit. And it's interesting where your error will come. It's always, of course, your models are bad always. If not, it's not a model. It will be reality. And you want to understand where your mistakes are coming from and where your noise is coming from. We have two types of noise. Some of the noise is coming from the measurements, blah, blah, blah. The worst noise to deal with is that we fit in meteorological weather predictions, numerical weather predictions as the weather forecast. But the weather forecast is not exact. So even in our training set, when we said in the past, the wind was like this and the prediction was like this, but we don't know what the wind was like. We know what the wind prediction was like, but nobody didn't really know what the actual wind was. They do reanalysis. That's what, again, will come up in their next talk, and that has more quality, but it's difficult to use for other reasons, or not interesting for other reasons. So we got noise in the input. We don't really know what was the wind situation happening. And of course, you always get some noise on the output, but in this case, this is our main error. And then we get the noise both in the training set, we don't know what happened in the past, and also when we predict based on the weather forecast, which is not exact. So, by the way, the weather forecast is science fiction after 5 days. because it's a science fiction. And yeah, tools to deal with this is just they generate not only one prediction, but an ensemble of different possible predictions. There's a notion that has been very useful for us. That was what was called before the poor man ensembles. Is like you take all predictions as other possible predictions, and yeah, that's like kind of technical tools for those of you who might know a little about this that have been very useful for us. And yeah, that's what I have to say. Thanks.
Okay, thank you, Ignacio, again. If you have questions, keep them for a while, and in some moments we will have time to chat. Well. And the last speaker of tonight is Ferran Alet, who is a research scientist at Google DeepMind, working on machine learning for science, particularly weather forecasting and mathematics. Ferran will show how graph neural networks trained on larger scale dataset can predict global weather forecasting at the state-of-the-art level. Ferran is not here physically, but he will join us through the video. So we hope everything works.
Can you hear me correctly? Yes, no?
Yes, we can hear you.
Okay.
And we can...
And you can also
see
see
you?
my face, right? Yes? Okay.
Okay, now we can hear you and see you.
Okay, I can only hear the microphone. Everyone else I cannot hear, just in case.
Yeah, everyone is hearing you.
Okay, cool. Thank you.
Thank you.
Cool. So I'll talk about graph neural networks for weather forecasting. In spirit, it's quite related to the previous talk by Ignacio. So in particular, I'll talk about two stories in 3.5 papers. I'll go a bit fast, but only glancing at the details of each paper. The first one is actually, I wanted to make a contrast from when I didn't have as many resources when I was doing my PhD. And we had a paper called Graph Element Networks. The second one is going to be about GraphCast, which was about using graph neural networks for weather forecasting. And the third one is a more recent one, which is called GenCast, which is using diffusion on top of graph neural networks. And diffusion, for those of you that have seen DALI or Imagen, is also behind a lot of these generative AI applications. So the two stories that I want to talk about is, the first one is structured in machine learning, and the second one is impact in machine learning. So when should we build priors or kind of biases into our models? And the second one is, what does impact look like in modern machine learning? And I mentioned 3.5 papers because it took us 6 months to go from regular GraphCast that we put on archive to science GraphCast. And I'm going to also talk about the difference between both. So let's start by this paper that I did at MIT with some colleagues there. The inspiration is that convolutional neural networks are a useful inductive bias in this case because they exploit structural properties like locality and shift invariance that, as it was discussed in the previous talk, they're useful for computer vision. In our case, we're interested in graph neural networks because in this case, they're a useful inductive bias because they exploit the fact that entities exist, and when you model them in a graph, they're permutation invariant. And this is satisfied across a broad set of tasks that model entities and their relations. So the field started in 2007, modeling web page and citation graphs. And then people started using it in molecules, as well as physical interactions like bouncing balls. And in my PhD, I realized that this could also be applied with partial differential equations and also models of the weather. Like in particular, imagine you have the Earth, right? It's its own metric space, and we have a function that goes from any location on the Earth to the input function. Let's call it the humidity and winds today. And we have an output function that predicts the probability of rain tomorrow as a function of space, any point on Earth. Usually in machine learning, we would learn a single function, right? Like going from an image to whether it's a cat or a dog. But in this case, it's a bit funny. We have a function that transforms another function. So we have a kind of a functor that goes from F to G. And in particular, we have samples to model these functions. As discussed in the previous talk, we actually are inspired by finite element methods. They're widely used in engineering, and they decompose the space into small regions, essentially embedding the problem as a graph. They have two nice properties. The first one is that you can trade off compute with accuracy. So you can have very few nodes and then not be very accurate, or you can spend more compute and be more accurate. The second one is that you can focus compute where it matters most. So if this area of the space is boring, you can allocate very few nodes. In some area is very hard, you can allocate a lot of nodes. If we think about where does this fit in the story, you can see that we are kind of repurposing graph neural networks, which were used for molecules and things like this, in a new problem setting. But it was also a relatively toy problem. So in particular, we have these input samples and output queries in a metric space, and we have these in discrete points in these spaces. And we go through, as often happens in deep learning, through a latent space. And in our case, it's going to be a latent function. And the way we're going to do this is by embedding this space where the function lives inside a graph. And we're going to parameterize this function. So we encode the input samples into this latent space via neural network encoder. We then propagate the information via a graph neural network. And this graph neural network has edge neural networks and node neural networks. And the key thing here is that each edge has the same edge neural network, and each node has the same node neural network. Therefore, there's a lot of parameter sharing that enables data efficiency. And finally, once we've processed this via message passing, we decode into the output space. As I was hinting, actually, the problems I applied it to were very toy. Actually, we applied it to the heat equation, partial differential equation. So imagine if you were given the external temperature of a room and where the heaters were placed, and you wanted to predict where the temperature is going to be at any point in space. It looks like the weather, but it's just a simpler problem. And our graphs, as this figure indicates, they were only 7 by 7, so about 50 nodes. So very, very small. But already in those experiments, we were able to already show the promise of graph neural networks for PD-like equations, like the property of training off compute with accuracy. You can see the green curve going down as we expand bigger graphs. And if you wanted to optimize the positions of where these nodes matter to focus on harder regions, we also saw that the optimized mesh worked better. Now we're going to focus on GraphCast. So I've shown you the toy problem. What did it look like in terms of application? So we have now our goal in GraphCast was improving global weather forecasting. So not local, like mostly in the last talk, but at the same time, probably a bit lower resolution. Still very high resolution, but not as precise as like, is it going to rain in a beach? Like more like on a 30 by 30 square. But we're going to do that 10 days ahead and everywhere in the world. And we have many variables. So here I'm showing surface wind, surface temperature, and temperature at a certain altitude. And we have more than 200 weather variables like this. And the intuition is that machine learning hopefully can do better than regular physics. And the intuition is that because, as it's been mentioned before, there is noise in the data, and also there is noise in the computation itself because we're making a lot of approximations. Maybe machine learning can learn this better approximate physics directly from data, even though we technically know a lot of the physics of the weather. So there's a question on why now? Why am I giving this talk now and not in 2015 and not in 2027? So there's been 3 key enabling factors. The first one is the ERA5 reanalysis dataset, which is a massive dataset, similar, like not as much as like the hundreds of terabytes per day that were mentioned in the first talk, but still pretty large. 4 years of data, and this data is super high quality. And the second one is compute. So we are kind of privileged to have lots of compute. In this case, this research took about, we were training on a mini cluster of 32 TPUs, which a TPU, you should think about it as like a modern NVIDIA GPU, but for Google. But we are replacing something that is also super compute intensive. So in practice, weather centers are using clusters of 10,000 CPUs and multiple hours, we now make predictions in a single TPU minute. So in some sense, compared to the average user, we have a lot of compute. Compared to weather centers, we actually don't have that much compute. We are saving compute. And the third thing is progress in deep learning algorithms. So in particular, we're using graph neural networks, but there's been other people that have used convolutional neural networks, Fourier operators, or transformers for similar problems. One thing that has been also hinted at in the two previous talks is that weather outputs are very large. In particular, we work at 0.25 latitude longitude resolution. If we think about MNIST, which used to be the main data set in 2008 or so, this is how it would look like. Then we went to ImageNet roughly, and then a single ETA 5, this weather variable, would look like this, so much higher resolution. But whereas ImageNet only has a red, green, blue channel, we have 227 variables, right? Because we have surface variables, but also 37 levels of the atmosphere. And we're not just predicting kind of an image of 200 channels, we're also predicting kind of a video. So we have multiplied 40 frames, so that adds up to like 30 gigs, which is roughly, we think it's one of the largest output examples ever used in machine learning. So how does it look like? The architecture is quite related to the one I was already talking about in the first paper. We get the input weather state, we pass it through a graph neural network that has this encoding to a latent state, then the message passing along a multi-mesh that uses the graph neural network to process, and then we decode back to make the final prediction. And it's autoregressive in the sense that when we want to predict, let's say, 2 days ahead, we actually predict 6 hours at a time. So first we predict 6 hours into the future, then 12, then 18, and so on. And finally, we design a particular graph on which to process, right? So this graph is, because we're solving a partial differential equation, we, as I was alluding in the first paper, we can design the graph whatever we want. And in our case, we designed a graph that had a few long-range connections to propagate the weather very fast, but also most of the connections, there were many, many connections that were local. And we essentially did that via starting with an icosahedron and iteratively dividing it by dividing its edge into two. And so we had lots and lots of local edges and a few global edges. And compare this to the first paper where we had 50 nodes. Now we have 40,000 nodes and 300,000 edges. So really, it scaled up by like 3 orders or 4 orders of magnitude in terms of edges. The results were very, very promising. So here you can see our forecast, our median forecast, and the median forecast of HRES, which is the gold standard physics-based predictions. And you can see that essentially they look the same. So let's look at it quantitatively. On the x-axis, you have number of days, and on the y-axis, you have the root mean squared error, in this case of geopotential 500, which is a measure of pressure, which is very standard in weather. And you can see that both curves go up with time, which makes sense. Predictions get worse with time. But the nice thing is that GraphCast has lower error than HRES. It's maybe easier to look at the percentage of improvement of GraphCast compared to HRES. And you can see that it ranges around 10 to 30% of improvement. And I'm showing you one variable, but there is many, many variables, and on most of them we're better. There's so many variables, right? There is variables, then levels of the atmosphere, different altitudes, and then also lead times, that it's better to aggregate them in colors. So the deeper blue would mean high improvement, small blue would mean little improvement, and red means worse. And you can see here that GraphCast is better on 90% of the targets because the scorecard is mostly blue. I'm showing here 90% scorecard. Internally, we have 97% because we essentially realized that just reweighting the loss coefficients, then we solved most of the problems in the high altitudes. And again, one of the key things that we needed to do was autoregressive training. So basically, we trained the neural network to predict the weather, let's say 1 day ahead, when composed with itself 4 times. We see that there is a trade-off where we can, if we train to do that, we're going to do slightly worse on 6 hours predictions, but that enables us to use the same parameters to predict 6 hours ahead or 3 days ahead or 10 days ahead with the same parameters, and that's very efficient. So if we look at the lessons of this paper, we see that we are encoding structure in machine learning via graph neural networks as before, but also autoregressive and multi-scale graph neural networks. And the impact now is not just a toy problem. Now it's very exciting, very promising results. Let me jump to a GenCast. And GenCast is the idea that before there was this joke about the forecast beyond 5 days being science fiction. It's true that because weather is a chaotic system, predictions are fundamentally uncertain. So if you give a single prediction, it's essentially made up because there is lots of noise. You cannot guarantee what's going to happen. So it's better to give an ensemble of different things that could have happened. That could happen in the future. And this will model the joint distribution of weather over space and time. So in particular, we do a conditional diffusion model where we condition with the current input frame. So when you go to Imagen or DALI, you condition with a sentence and you generate an image. In our case, we condition with the current weather and we get the future weather. And whereas GraphCast was deterministic, now GenCast is probabilistic. And again, we could have rolled out GraphCast more than 10 days, but it wouldn't make sense because the predictions were already pretty bad. GenCast now makes good predictions up to 15 days. And the intuition of how diffusion model works in our case is basically we start with noise and we iteratively clean up the noise. So at training time, we add noise to the ground truth and we train a model that essentially removes the noise. And you do that by steps, and that's the TLDR of how diffusion works. Okay, another nice thing is that we didn't have to change much, both in terms of diffusion. We follow the elucidated diffusion model framework by Karas et al. The only change we made was that noise usually in images, it's a flat image, a flat rectangle. Here we are dealing with a sphere, so we added white noise on a sphere instead of an image of like a rectangle, so the noise changes a bit. And the denoiser architecture is largely based on a GraphCast. On the GraphCast architecture, we changed the graph neural network for a sparse transformer. It looks really the same. It's just about how the connectivity is essentially the same, is very similar, and the type of message passing is slightly different. But I don't think that matters really much. It was mostly a speed issue. So as I was saying, GraphCast predictions, if you look at the second row, 10 days in advance, are very, very blurry. But we would like to have samples that are quite realistic. And you can see GenCast here. Each sample, so column B, column C, column D, have a very high level of detail. And then if you do want to get the mean of what's going to happen, you can average them together and get a blurry image. But here on the right, you see a spectral power that whereas GraphCast in pink loses a lot of spectra on the high frequency content, you can see that GenCast keeps predicting realistic images. Not only that, but we also do very, very well in terms of ensemble Rudman squared error and also on CRPS, which is a probabilistic measure. And before the comparison, the baseline was the best deterministic physics model, but now the baseline is already the best probabilistic physics-based model, which, as far as we know, is the best global weather model in the world. So really, we are showing that we can do better than the previous weather model in the world. And now, I would say it's very likely that machine learning has essentially surpassed physics models in terms of global weather modeling, with some caveats that I'm going to talk about later today. And also, some people think that there may be some risk about, especially on extremes, right? So like very high wind, very high temperature, but also we do pretty well on that as well. So again, here in terms of structure, we have added diffusion and sparse transformers. In terms of impact, is a bit similar to GraphCast in terms of like exciting results. We are beating physics baselines. So in terms of GraphCast to science GraphCast, which we were very happy to get the cover last December, what was the difference? And I think it was very inspiring for me to see it from the inside, in the sense that the main difference was literally just real world impact, which goes pretty well with the topic of this conference. So it was about showing that the metrics, that the RMSE results that I was showing you mattered for the real public. So in particular, we were talking about extreme heat, a bit related to the dengue outbreaks that we were talking before, in the sense that, of course, temperature is going to be increasingly a problem with climate change. And we saw that GraphCast was better at predicting heat extremes and heat waves than physics models. And then we also looked at tropical cyclones. That's been studied that tropical cyclones are going to increase with climate change, both in its frequency as well as in its intensity. And it would be good if we could essentially warn people a few hours or even a day before than current physics models, right? And we saw that indeed GraphCast, even though it was not trained specifically to predict cyclone tracks, it was trained to predict general weather. It was also pretty good at predicting the movement of cyclones, gaining about 9 hours of accuracy. And one cool thing is that we have open sourced the weights of the model and the forecasts already. And just after we open sourced them, there was Cyclone Lee in Nova Scotia. And the press started kind of talking about this cyclone because it would be the first one where machine learning and physics models would kind of compete in the real world. And we were a bit lucky because we win more than we lose, but I think it's a bit 50-50. And in this case, we won by quite a bit margin, like roughly locating the right place of landfall 9 days ahead. We've started to have real world impact. You can have the code and the weights in these QR codes, and we were also happy to see that the community of AI for weather won the science breakthrough of the year. Sorry, just a finalist, not won it, but still very, very exciting. And finally, to conclude the point about structure in machine learning, there was this also discussed in the previous talk about being aware of the space, right? So there is MLPs, transformers, sparse transformers, graph neural networks. Even we could have gone even deeper and leveraging the spherical properties of the fact that the Earth is essentially a sphere and there is some symmetries that we are not exploiting. And then thinking about the trade-offs, right? So graph neural networks enable more data efficiency than, let's say, transformers or sparse transformers, but sparse transformers have a nice fit with the TPUs, so they run faster. So it's a mixture, and one has to think about these trade-offs. And finally, it's also worth pointing out that there is one inductive bias that we are leveraging quite a bit, which is the fact that our training data has been generated with physics inside. And so that also is worth taking into account. It's not full replacement of machine learning for physics. So that concludes the two stories. I wanted to thank my collaborators, both in the GraphCast paper and the GenCast paper, and thank you all for your attention.
Okay, thank you, Ferran. I don't know if you hear the applause. Now let's start with the Q&A for everyone. So I invite the speakers to come again to the stage. Okay, just for Ferran to see the audience.
Thank you.
It's very crowded, so I will leave the cam open so you can see how the other speakers and yourself answer the questions. Okay. Okay, we can leave it like this. So thank you, everyone. I think that it has been a very enriching session because we have seen like the same problem from very different perspectives. And I would like to start asking a question for all of you regarding one of the last points that Ferran made. Are we close to replacing all the traditional models based on physics and chemistry to only use AI or machine learning? Who wants to start?
No. There are several reasons for this. For weather, the reasons are different than for climate. For climate, the reason is what I mentioned before. So it's very difficult to build a machine learning based model for the whole climate system, because you need a model for all the components. You need a model for the ocean, and we don't have satellites in the ocean, so we have very little knowledge of what happens below 2,000 meters, and there is a lot of water below 2,000 meters. We know very little about how the ice sheets are behaving in Antarctica and Greenland. Very little data, very little knowledge. We need process-based knowledge for this. And there are other components. The chemistry in the atmosphere, it's really largely unknown for many species. So yeah, basically we need data, and the data is not there. As Ferran said, ERA5 is a fantastic resource that really made the explosion of all these generative models for weather forecasting. But we don't have the equivalent for the ocean and the other components. For weather, and this is my opinion, personal opinion, I don't think it will happen, at least not with private-based machine learning models, because weather forecasting is, in the end, it's a political. It's very politically loaded, because civil protection is very much related to it. Alerts can only be made by weather services, and these are public entities. And in the end, weather forecasting is a defense problem, and defense will never, at least in Europe, it will never be on private hands. So what seems to be likely is that machine learning based models will be developed most likely in collaboration with the companies like Google by weather services themselves.
Thank you. Want to add something?
You said a very assertive no. I'm more doubtful. About that question, it's like the same about ChatGPT. How you say metaphora in English? Metaphor. That's the comparison works in my mind. Somewhere in the 80s, there was this big competition between Kasparov and Deep Blue. Many of you were not born, but I was there. And yeah, first time Deep Blue won. No, Kasparov won the first one. Second one, Deep Blue won. I was in the 80s. And yeah, now my cell phone can beat Kasparov and everybody. So once, my opinion, my mind is that, so the progression of humankind is what it is, and the progression of machine learning we still don't know. And once it is almost level with some state of the art of whatever, very soon we'll be way past. And that's my wrong. That's my view. So I'm not, so science itself is going to change a lot, because science itself is going to be very impressed by machine learning. I think distinction is going to become more blurry. But yeah, I don't know.
Okay, Rachel, Ferran, do you want to add something?
I can add something. So my answer is a bit in the middle, probably, of both. I agree that with the climate probably requiring a lot of physics, at least in the short term. The reason being, but the reason is a bit different than the reason that was proposed. I believe that there is not enough data, and the reason being, and that's true for climate, and it's not really true for weather. I think there is a lot of data for weather. The issue is that at climate timescales, then it's essentially all correlated. And if you're interested in like making 10-year predictions, then really independent samples, you only have like in the last 50 years, you essentially only have like 5 samples, right? Like you only had 5 decades. Of course, there is like lots of pixels. I'm simplifying a lot, but you have a lot of one-day predictions. You don't have that many one-decade predictions, and you have essentially 0 100-year predictions. And also, like there is a lot of like decision making. How much CO2 is going to be pumped up? When you look at our data sets, there is a lot of distribution shift. Like you can see temperature increasing inside our data set, and we also have experiments that if we only train up to 2018. We do worse on 2020, then even worse on 2021, and so on. And we need to keep retraining. So there is this issue. I don't think it's an issue as not knowing the chemistry of the atmosphere or some things, and that's not inherently an issue. And that, if anything, that would be something that machine learning has an advantage over traditional models, because machine learning doesn't need to know the full chemistry or the full processes. It just makes approximate computations. It doesn't even need to be physics. So in that sense, I think that's an argument in favor of machine learning. Similar to Ignacio, I'm also like kept being surprised by machine learning. It's like eventually you say, okay, if I've been surprised 5 times, I should probably start changing my priors and assume let's keep going to improve. And like we visited the European Weather Agency a year ago now, and they were very, very skeptical. But credit to them, after seeing the results, they started their own machine learning lab inside. I agree that there's going to be a lot of collaboration with kind of public agencies, because as mentioned, it's a matter of public safety, and that doesn't mean that it's probably going to be machine learning based a lot, especially in weather. Probably climate, no, but weather a lot. It's still, the data sets come from physics, the observations come from physics. It's worth mentioning that it's not physics machine learning end to end. Our data sets are physics, our sensors are physics, the satellites have to do physics.
Okay, thank you. Following what Ferran just said, that at the end we need this data, and we have plenty of data for weather prediction. For the models that Rachel you presented for the spread of disease, in particular in these countries like Vietnam that you showed, how sensitive are all these predictions to the actual quality of the data that you can find in these regions?
Yeah, they do depend very much. So, rubbish in, rubbish out. So the quality of the models depends, on all the different data we're feeding into them. And we have done some experiments to see the different outcomes we can get from the health impact models, for example, for dengue and malaria, if we're using a range of different gridded or satellite products compared to actually using data from a weather station that's, in the city where the transmission's happening. And we can find quite different answers in terms of the proportion of the relative change in relative risk from 1 degree increase in temperature. It could be a difference of up to 20%, depending on the data set you're using. So it does make quite a big difference, the inputs you formulate the model with. And then when you start using, that's using reanalysis or observed climate data. And then once you start using forecasts of the climate, you're adding additional layers of uncertainty, which you then have to also account for. So we do find it has quite an impact on the outcomes of the models. And that's why a lot of these products can't just be taken off the shelf. You have to apply a lot of sort of post-processing and understanding the local context in which you want to predict.
Okay, thank you. Now let's open the questions to the audience. So here.
Can you hear me? Yeah, perfect. So, well, mainly my question is, what do you think it will be the role sorry about that, of AI, both maybe hybrid models or purely data-driven ones, when it comes to larger timescales, weather models, but in larger timescales, that is subseasonal, seasonal ranges, because we've talked about models and there are plenty of them, Pango Weather and GraphCast coming out up to just 15 days, even though ensemble based. But what do you think may be the role for these kind of technologies in these time scales? So yeah.
Okay, I shouldn't be that arrogant this time. So no, there are very good examples of the use of machine learning for subseasonal and seasonal forecasting. In particular, because you can develop simplified models for the main drivers of variability at those timescales in the ocean, which is something that works quite nicely. Actually, that the initial papers already 5 years ago were about the prediction of El Nino with machine learning models, and it worked quite well. So for that kind of application, I see a really nice future, because the observations in the particular parts of the climate system that matter, in particular the troposphere, the lower stratosphere, the upper part of the ocean, are relatively good. So the training and the sample, as Ferran was pointing at, so the sample is much bigger than if we go to climate timescales, where basically we have one sample if we are looking into the long-term future. Yeah, really nice. There are very nice applications now emerging for this.
I can add a bit in this line. There is a paper coming out of Google, but I'm not a co-author, called Neural GCM, which does something a bit in the line. It came out late last year, which basically what it does is essentially it implements a simplified weather model, that's the general circulation system, in JAX, so it's differentiable, and then it adds a few, I think it's just MLPs, making corrections on top of this simplified weather model. And the premise of the paper is that they get the best of both worlds, right? So it's they have the inductive bias of just implementing a weather model, and then they still get the feedback from the data. I've also worked, like my background, actually, I studied math and physics in at UPC. So I'm very kind of sympathetic of like merging physics and machine learning, and there's ways to kind of, for instance, encourage predictions to satisfy energy conservation or other laws of physics, and I think that also has potential to kind of, especially to ensure that predictions are still meaningful. Like for instance, this Neural GCM paper was showing predictions were stable even a year into the future and things like this. Still, when feeding sea surface temperature as a forcing, so they were not predicting oceans, as was mentioned, it's quite hard. But assuming they had this ocean, that the model was still stable at subseasonal ranges.
Thank you. More questions?
Hello, question for Rachel. You mentioned many times how you work, how you transform and experiment with weather data. But what about data from the hospitals? Because in these Southeast Asian countries, especially far away from the big cities, places, medicine is not very well developed. Dengue, since it doesn't have any cure, so people just maybe stay at home, so they don't fix these cases. So maybe it can affect, and also easily advertisement of a new mosquito spray or anti-mosquito net can impact very much. So did you consider something like this about that?
Thanks for the question. Yeah, we do. Where we can, we try and take into account things like interventions or apply corrections for asymptomatic cases. So if we have actual data to measure those things, we can incorporate them into the model. So recently we developed a prediction model for Singapore, which is one of the places that has the best surveillance data for dengue. and they can tell us what is the particular serotype of the dengue virus, and that helps us detect outbreaks that may be more due to lack of population immunity rather than some big El Nino event changing the temperature conditions. So if we have the data, we can include it within the model, and where we don't have the data, then we can use random effects in our model and look at sort of the shapes of the distribution of the factors that we can't measure or explain in the model, and then we can share that with our stakeholders, and then they can say, oh yeah, that was the year where there wasn't such a intensive intervention, or there was some sort of interruption to. And we can include factors for issues to do with access to healthcare, things like distance to the nearest clinic, and so where we have the data available, we can certainly incorporate it to help better quantify the association between the climate variation and the disease outcome.
A question for Francisco. Building a digital twin is very complicated. I work building digital twins for the financial sector, and it's less complicated than probably the digital twin of the world. I just want to have more insights about how did you build the digital twin. I imagine you use, as you mentioned, a lot of science, a lot of research. But if you can give us, let's say, like for dummies, how the digital twin of the climate operates. And also, in these digital twin exercises, edge cases help a lot to understand what can happen in the scenarios that we model. And I would like to understand this sort of, or if you can give us also some sort of understanding of those edge cases. Like, I don't know if the model is able to do some sort of analysis, like what if all of our houses just turn off the light for 1 year, and what can happen with the world, or these sort of things. But I would like to understand a bit more about this, if possible. Thank you.
Yeah, these are two very long and complex questions. So how do we build the digital twin? It's a lot of software, basically, as you might have done as well in your case. What we found the most complicated is not really the software part, is how to integrate the possibility for the users to interact with the digital twin. That's where the tricky part comes in. In particular, because what I said during the presentation is that the climate adaptation arena is very complex. It includes myriads of sectors, with each one of them with a lot of many different actors with different priorities, values, and contexts. And that's where we are really trying to find a way to generalize this as much as possible. So far, we don't have a solution. So what we are is picking representative actors in different sectors, in particular policy making, and trying to make sure that we can identify really key questions from them that are not being addressed by the current producers of climate information. The example that I gave for the European Commission going to the negotiation meetings, not having timely sources of information to really make decisions is one. It's an obvious example, mainly because it's paid by the European Commission. So we really need to address their questions. But to generalize this is very complicated, and there are solutions that are being addressed, and that will allow us to make sure that we are providing all the relevant variables that the users are expecting at the adequate frequencies with the right experiments that they are asking, and that relates to the second part of your question. How do we try to infer what happens into the future? So basically, we work on the basis of scenarios. So what are the scenarios that are plausible for the future? And those scenarios include possibilities that could be, well, they are infinite somehow. What happens, and with the workshops with the different directorate generals at the European Commission, we have been identifying some of the relevant scenarios for them that are not being considered right now. And those scenarios emerge from actual futures or potential futures from the socioeconomic point of view. So what happens if there is a regional war? What happens if there is a global war? Probably if there's a global war, climate is not our main problem. But what happens if the European Union disappears? So the European Union is considering the possibility of the disappearance of the European Union, which is it's really interesting to see this. And all these different questions can be translated into different potential futures that correspond to emission scenarios. So how much more CO2 and methane and nitrous oxide is going to be emitted in the next 20, 30, 40 years if the European Union disappears. Most of the mitigation targets will be gone. Many countries will start emitting like crazy just to catch up as well. Look at the UK, what happened when they leave in the EU. So there are lots of political decisions that can be transformed into scenarios that correspond to emission scenarios that will define the climate trajectory that we will follow. And that's what we are trying to do. It's mainly the user requirement that is very, very tricky.
Okay, we have time for a last question. I think here in the front they asked before because the pizzas are getting cold. So let's cover this question, and we can keep chatting later with the refreshments.
Thank you very much. I'm curious about when you have the meteorological models, and maybe the question goes as well for climate models. If there's anything you input for meteorological models, anything about climate change, how do you handle that? How is that reflected? Does it affect already, even if it's a shorter time span? And also I'm thinking about like different regions, because I've seen like public communication saying, oh, well, now in the next 10, 20, 30 years, the temperatures that you have now in Valencia, you're going to see them in Paris. So if that's something that you could input into your models, is that something you don't want to or want to input, or is that more of a result that you get and that then is used for communications like this? Thank you.
Ferran, this probably was shooting for you, but I will start.
Okay,
And I will use my turn also to, because he said was the last question, I wanted to ask you a question. I think a speaker can ask another speaker. Yeah. So I will use the microphone then to pose you a question before as far as I understand it, and the more data-driven you are, the less chance you have to plug in a model. So if you want to plug in additional information that is not data yet, if you are doing it only data-driven, you can't somehow. Then, yeah, that would be like the short question. But I will give you a better one. But I wanted the microphone to ask him also. I want to know how do you do predictions now? Because I understand your predictor is working now, and the way I understood, we studied your paper. It was wonderful. And the way I understood, you for any given prediction, you need to fit in all the actual meteorological variables, so all the actual data. But of course, that data, not all of it is physically measured. So it is predicted by a previous model. So, right, is your model right now making predictions? And if so, how do you feed it?
Yeah. Okay. So
answer to her first, because she was first.
No. Yeah. So I don't know a lot about climate in machine learning. From the machine learning point of view, what I can answer. Can you still hear me well? Because I think I disappeared from the screen first.
Yeah, we can hear you.
Okay, sorry.
Okay, we can see.
Okay, thanks. From a machine learning point of view, I'm pessimistic about out of distribution generalization. I think the reason that ChatGPT, Gemini, and so on have worked very well is because they just train on everything, right? If you train on the entire internet, then you generalize. But then out of distribution, goodbye. And so climate, if we want to climate change, then I'm quite pessimistic. So that's my short answer to the first question. To the second question, it's a bit kind of what I was alluding in the last slide, the fact that we are still under the hood using physics. So the way I think about it is the past, we are using the data set right from the past of ECMWF. The European agency is giving us 50 years of data. The present, also we use European agency, or like, I think it's the European agency, maybe it's someone else, that assimilates the weather, takes all the sensors and gives us the weather, not now, but actually 3 hours ago. But that's not just us. Every as you probably know, every weather model assimilates all the sensors, goes back some amount of hours and says, okay, if all these sensors, both 6 hours ago, 5 hours ago, and up to now, I got these sensors, that must mean that I can kind of do some analysis and data assimilation and extrapolate the temperature and wind everywhere. Of course, I'm going to make mistakes. It's going to be noisy, but you make an approximation. And then from these data, we may start making predictions. So we are making live predictions right now that you can find in the European agency, that under the hood, we wait for them to give us the present, and then we make hopefully better future predictions. I cannot.
And you are 3 hours late. You have a 3 hour latency time.
Yes, but the everyone is 3 hours late.
Yeah. And then the last question, is that public information? So can I get access to that information?
Yes. You can cool. Get access even to our weights, as far as I know, and you can get access to the forecast as well. Pretty sure. Like images for sure. Like if you don't want raw numbers, for sure, because I've done it. I've looked at it myself. But I'm pretty sure that but it's through the European agency that they just have a tab where you can say GraphCast and you look at GraphCast predictions. And they have their own model. They have like their model that they did a model on top of GraphCast, sorry, not on top, but like inspired by GraphCast called AIFS. They also have their own predictions and so on.
Thank you very much. I'll write to you.
Okay.
For sure.
Okay, thank you. A huge applause again for our speakers. And thank you very much for being here, the four of you. And now for those that are like live in the office, we have some pizza and drinks in the other side of the corridor, so we can keep the conversation in there. Thank you for coming.
Bye, thanks for having me.